MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we'll work a problem on hypothesis testing involving the population proportion, and it will be a two-sided test. The problem setting is the following. A university found that over the years, out of all the students who are admitted, the proportion who accept is 70%. After a new director of admissions has been hired, the university wants to check if the proportion of acceptances has changed significantly. Suppose they offer admission to 1200 students and 888 accept. Is there evidence of a change at 5% significance? First of all, the 5% significance, or alpha equal to 5%, means I'm willing to accept a 5% chance of making a type 1 error, that is, rejecting the null hypothesis when in fact it is true. So notice that the population here is the set of all admitted students to this particular university. The population parameter of interest here is P, the proportion of those admitted students who actually end up accepting. The first step in doing hypothesis testing, as always, is to set up the null and the alternate hypothesis. And remember the important guideline that I mentioned in several of the problem settings earlier, is that we set up these hypotheses in such a way that the result we want to establish preferably should be the consequence of rejection of the null, because the way we do hypothesis testing, we are minimizing the likelihood of a type 1 error. In other words, we tend to be relatively certain of our conclusion when we end up rejecting the null, not the other way around. So in this case, the result I want to check, or the condition I want to check, is whether or not the proportion of acceptances of these students has changed significantly. Therefore, that result, that outcome, I would put as the alternate hypothesis. So P not equal to 0.7. And why did I put it as the alternate? Because if this result, P not equal to 0.7, is established, that would be a consequence of the rejection of the null. Okay, hence my null hypothesis is P is equal to 0.7. So that's my null and alternate hypothesis. Notice that the alternate hypothesis is a two-sided test. In other words, I could end up rejecting the null either if P is significantly higher than 0.7 or if P is significantly lower than 0.7. That's why this is a two-sided hypothesis test. So since we are doing a hypothesis test on the population proportion, the sample statistic that I would use is the sample proportion P bar, which in this case is 888 acceptances out of 1200, which is 0.74. Okay, so that's the sample statistic. So then my point estimate of the population proportion is of course 74%, but we want to do a hypothesis test over here. Remember that since the sample statistic being used for the hypothesis test here is the sample proportion, if the sample is large, meaning if these two conditions are fulfilled, n times p greater than or equal to 5, n times 1 minus p greater than or equal to 5, if those two conditions are met, then the sample proportion p bar is distributed normally, as you see over here. And what would be the middle of this distribution, the expected value? All hypothesis testing starts with the assumption, what if the null were true as an equality? Would I be seeing as extreme a value that I saw in the sample? So if the null is true as an equality, then P would be 0.7, hence the expected value of P bar of the sample statistic would be 0.7. And the standard deviation of the sample proportion, sigma P bar, you recall the formula is square root of P times 1 minus P divided by N, which would be square root of 0.7 times 0.3 divided by 1200. Okay, notice that in the expression we use the value of 0.7 as P, not 0.74, because as I mentioned, all hypothesis testing starts with the assumption that the null is true as an equality. So we must use, if the null is true as an equality, then P must be equal to 0.7, not 0.74. So let's see what this turns out to be. SQRT of 0.7 times 0.3 divided by 1200, which is which is 0.013. So we'll keep that in hand for future calculations. Now we'll try to work this problem both ways, once with the critical value method, once with the p-value method. The critical value method tells us that we first find out the critical value. In other words, how large does the test statistic have to be? How extreme does the sample statistic have to be in order for us to be over the threshold of our 5% limit? So look at the z critical over here. It's a point on the x-axis which says I have to be so far away from the middle 0.7. I have to be a certain distance away for the test statistic to be called extreme. And how far does this critical value have to be? It has to be far enough away such that the area to the right is 0.025. Why 0.025? This is a two-sided test, okay, and I'm willing to accept a 5% chance of making a mistake. So that splits into 2.5% on the upper end, 2.5% on the lower end. So the z critical in this case, to realize how far away I need to be from the middle in order to be called extreme, this would be norm S inverse of 0.975. Why 0.975? Because the area to the left of z critical is 0.975. okay, that's the input that Excel needs. So that's 1.96. So z critical is 1.96, meaning the test statistic has to be at least 1.96 standard deviations to the right of 0.7 in order to be called extreme. So let's see what we actually have from the sample. The sample statistic that I got is 0.74. So is that far enough away from 0.7? So that would be 0.74 minus 0.7 divided by 0.013. 0.013. So that's the test statistic. In other words, I'm normalizing what I got from the sample to see whether it's extreme enough. Okay, so where does that get me? This would be equal to 0.74 minus 0.7 divided by 0.013, which is the standard deviation of the sample proportion, okay, which ends up being 3.07 standard deviations out. So z, as you can see, z is somewhere here. It's way past the critical value. Okay, so z is greater than zc. So the sample statistic that I got, which is 0.74, 74%, is way above what my threshold is to be considered extreme. My calculation of the threshold is 1.96 standard deviation. Tells me that any sample statistic that is more than 1.96 standard deviations above the mean, I would consider it extreme enough, meaning highly unlikely to have occurred by chance if the null were true as inequality. So my conclusion is reject the null. So I would say yes, as the result of this hiring of this new admissions director, the proportion of students who have accepted has changed from 70%, and in fact not only has it changed, I would go out more and say it has changed in the upper direction, meaning it has gone up. That's what the sample statistic seems to indicate. Now let's solve this problem the alternate way, namely using the p-value method. The p-value method simply says that if the null were true as an equality, what is the probability, that's the p, what the p stands for, what is the probability that I would be observing a sample statistic as at least as extreme as the one that I just saw. So here I simply want to compute the probability of p bar being greater than or equal to 0.74, and I would multiply that by 2 simply because this is a two-sided test. Okay, so by now you know what built-in Excel function I would use. I would use a norm dist function. So I would say equal to norm, well, let me use a norm S dist here, since I've already calculated the z value for the test for the sample statistic is 3.076. 3.076. Okay, so that's what the 0.74 is in normalized terms. So, and I'll multiply this by 2. So before I hit return, let's just go over what this calculation means. So this is this norm S dist of 3.076 multiplied by 2 is 2 times the probability of P bar being greater than or equal to 0.74. Again, remember why I multiplied by 2. It's simply because this is a two-sided test. The alternate hypothesis is P not equal to 0.7. And where did I get the 3.076? That's the sample statistic, the 0.74. Here you can see the 0.74 simply normalized. Okay, 0.74 minus 0.7 divided by 0.013, which is 3.076 standard deviation. You could just as well have used norm dist, but then you would have to plug in all those different parameters, 0.74, 0.7, 0.013, and you would end up with the same number. Okay, so this ends up being oh, I made a slight error over here. Norm S dist of 3.076 would be the area to the left of 3.76, and obviously I want the area to the right of 3.076. Okay, so it's 0.002098. So this is what's the p-value. This is the p-value. All right. So there's only a 0.2% chance. There's only a 0.2% chance that I would be observing a sample statistic as extreme as the one I just saw if the null were true as an equality. Since p is less than alpha, my alpha is 5%, I would end up with the same conclusion, namely reject the null. So since I'm willing to accept a 5% chance of making a mistake, that is rejecting the null hypothesis when in fact it is true, and the calculations that I have done here tell me that there is only a 0.2% chance that I would be seeing a sample statistic as extreme as 0.74 if the null were true as an equality. I would say it's highly unlikely that I got this by chance if the null were true. So I'll say, well, I'm very comfortable rejecting the null. My assumption on which this entire analysis was based started off assuming that the null is true as an equality. That assumption must be false because it's highly unlikely that I would be seeing what I see in the sample purely by chance. And the probability of seeing that is 0.2% that you can see over here. That's the p-value. Since p is less than alpha, the threshold of uncertainty that I have, I end up rejecting the null. Same conclusion that I got using the critical value method.